Moisture can significantly impact the performance of circuit breakers, leading to reduced insulation resistance. Moisture can penetrate the insulation around electrical conductors, reducing its resistance and increasing the risk of short circuits. Moisture can cause corrosion of metal components such as contacts and terminals, impairing their electrical connections. Moisture can create an arcing environment between electrical components, potentially leading to fires. Surface rust on the panel and rusty screws indicate exposure to moisture. While light surface rust may not significantly affect breaker performance, extensive rust can compromise the integrity of the electrical connections and increase the risk of failure. Based on the information provided, here are some recommendations. Firstly, inspect the circuit breakers for signs of corrosion or damage. Replace any breakers that show significant rust or other issues. Secondly, clean the panel to remove surface rust and dirt. Use a soft brush and a non-abrasive cleaner specifically designed for electrical panels. Thirdly, inspect and tighten all screws securing the wires to the breakers. Replace any rusty or damaged screws. If the rust is extensive or if the panel has been exposed to water damage, consider replacing the entire panel. A faulty or damaged panel can pose a significant safety hazard. Reduced insulation resistance is a critical concern when moisture is present in electrical panels and around circuit breakers. The purpose of insulation is to prevent current from flowing where it shouldn't, directing it along the intended conductive paths. Common insulating materials in electrical systems include polymers, ceramics, and specially treated papers, each chosen for their high resistance to electrical current. When moisture infiltrates these materials, it introduces a conductive medium, drastically reducing the insulation's effectiveness. This reduction in insulation resistance creates several problems. Firstly, it increases the risk of leakage current, where electricity strays from its intended path. This can lead to energy wastage and can also create dangerous conditions. Secondly, reduced insulation resistance makes short circuits more likely. A short circuit occurs when electricity finds an unintended, low-resistance path, bypassing the normal circuit elements. This results in a surge of current that can damage equipment, trip breakers, and even start fires. Thirdly, the presence of moisture can accelerate the degradation of insulation materials. Many insulators are porous to some extent, and moisture can penetrate these pores, leading to swelling, cracking, and chemical changes that further diminish their insulating properties. To mitigate the risks associated with moisture, several strategies can be employed. Firstly, maintaining a dry environment is crucial. This can involve using dehumidifiers in damp locations, ensuring proper ventilation, and sealing any openings that could allow moisture to enter the electrical panel. Secondly, regular inspections can help identify and address potential problems early on. Look for signs of moisture such as condensation, water stains, or corrosion. Insulation resistance testers, also known as megometers or megas, can be used to measure the insulation resistance directly. A significant drop in resistance indicates a problem that needs attention. Thirdly, proper installation and maintenance practices can help prevent moisture-related issues. Ensure that all electrical connections are tight and corrosion-free. Use appropriate sealing compounds and enclosures to protect against moisture ingress. Corrosion of components is another significant issue when moisture affects circuit breakers. Corrosion is the gradual destruction of materials, usually metals, by chemical or electrochemical reactions with their environment. In electrical systems, corrosion can severely impair the performance and reliability of components, especially those made of metal, such as contacts, terminals, and enclosures. When moisture is present, it acts as an electrolyte, facilitating the flow of electrons and accelerating the corrosion process. Different metals corrode in different ways. For example, iron and steel rust when exposed to moisture and oxygen, forming iron oxide, which is brittle and flaky. Copper, on the other hand, forms a greenish pattern of copper carbonate, which is more protective but can still degrade electrical connections. Aluminum corrodes by forming aluminum oxide, which is a good insulator but can create problems if it builds up on contact surfaces. The effects of corrosion on circuit breaker components are manifold. Firstly, corrosion increases the resistance of electrical connections. Corroded contacts and terminals have a reduced surface area for current flow, leading to higher resistance and increased heat generation. This can cause the breaker to trip prematurely or fail to trip when needed. Secondly, corrosion weakens the mechanical strength of components. Rust and other corrosion products can unbrittle metals, making them more susceptible to cracking and breaking under stress. This can compromise the structural integrity of the circuit breaker and lead to malfunctions. Thirdly, corrosion can interfere with the proper operation of moving parts. Circuit breakers rely on mechanical linkages and springs to trip and reset. Corrosion can cause these parts to bind or seize, preventing the breaker from functioning correctly. To combat corrosion, several strategies can be employed. Firstly, using corrosion-resistant materials is essential. Stainless steel, aluminum, and copper alloys are all more resistant to corrosion than plain steel. Plating or coating metals with protective layers, such as zinc or chromium, can also help. Secondly, applying corrosion inhibitors can slow down the corrosion process. These chemicals form a protective film on metal surfaces, preventing moisture and other corrosive agents from reaching the metal. Thirdly, regular cleaning and maintenance can remove corrosion products and prevent further corrosion. Use a wire brush or abrasive pad to remove rust and other deposits, and then apply a corrosion inhibitor. Lastly, providing proper ventilation and drainage can help reduce moisture levels and prevent corrosion. Ensure that electrical panels are located in dry, well-ventilated areas and that any water that does enter can drain away freely. Arcing and fires represent an extreme hazard when moisture interacts with electrical components. Arcing is the formation of an electrical discharge between 2 points, typically through a gas such as air. It occurs when the voltage between the points is high enough to ionize the gas, creating a conductive path for current to flow. Fires can result when the heat generated by arcing ignites nearby combustible materials. Moisture plays a significant role in arcing and fire hazards in several ways. Firstly, moisture reduces the insulation resistance of electrical components, as discussed earlier. This makes it easier for arcing to occur by creating a path for current to flow through unintended areas. Secondly, moisture can create conductive bridges between components. Water films or droplets can form on surfaces, connecting points that would normally be isolated. This can initiate arcing and create a path for current to flow through flammable materials. Thirdly, moisture can accelerate corrosion, which weakens electrical connections and increases the likelihood of arcing. Corroded contacts and terminals have a reduced surface area for current flow, leading to higher resistance and increased heat generation. This can cause the surrounding insulation to break down and ignite. Arcing can generate extremely high temperatures, often exceeding several thousand degrees Celsius. This intense heat can quickly ignite nearby materials, such as insulation, wiring, and dust. Once a fire starts, it can spread rapidly, consuming the electrical panel and surrounding structures. To prevent arcing and fires, several precautions should be taken. Firstly, ensure that all electrical components are properly insulated and protected from moisture. Use enclosures and sealing compounds to prevent water from entering the electrical panel. Secondly, regularly inspect electrical equipment for signs of damage, such as cracks, frayed wires, or corrosion. Replace any damaged components immediately. Thirdly, avoid overloading circuits, as this can cause excessive heat buildup and increase the risk of arcing. Use appropriately sized circuit breakers and wiring for the load. Fourthly, install arc fault circuit interrupters, also known as arc fault circuit breakers, to detect and interrupt arcing faults. These devices are designed to trip when they detect the characteristic current patterns of an arc, even if the current is below the normal trip threshold of the circuit breaker. Lastly, keep the electrical panel clean and free of dust and debris, as these materials can ignite easily. Use a vacuum cleaner or soft brush to remove dust regularly. Surface rust on the panel and rusty screws are visual indicators of moisture exposure, and they warrant careful attention. Surface rust is the formation of iron oxide on the surface of steel or iron components. Rusty screws are screws that have corroded due to moisture exposure, often exhibiting a reddish-brown color and weakened threads. While light surface rust may not immediately affect breaker performance, it signals an environment conducive to more severe corrosion and potential electrical issues. Extensive rust, however, can compromise the integrity of electrical connections and increase the risk of failure. The presence of surface rust and rusty screws indicates that moisture has been present in the electrical panel. This moisture can come from various sources such as condensation, leaks, or high humidity. The moisture reacts with the metal components, causing them to corrode and form rust. This rust can then spread to other parts of the panel, potentially affecting the performance of the circuit breakers and other electrical components. Firstly, rust can increase the resistance of electrical connections. As rust forms on contacts and terminals, it reduces the surface area for current flow, leading to higher resistance and increased heat generation. This can cause the breaker to trip prematurely or fail to trip when needed. Secondly, rust can weaken the mechanical strength of components. Rust can embrittle metals, making them more susceptible to cracking and breaking under stress. This can compromise the structural integrity of the circuit breaker and lead to malfunctions. Thirdly, rust can interfere with the proper operation of moving parts. Circuit breakers rely on mechanical linkages and springs to trip and reset. Rust can cause these parts to bind or seize, preventing the breaker from functioning correctly. In addition to the direct effects of rust, the presence of rusty screws can also indicate other problems. Rusty screws are often difficult to remove, and attempting to do so can damage the surrounding components. Also, rusty screws may not provide a secure connection, which can lead to loose wires and increased resistance. To address surface rust and rusty screws, several steps should be taken. Firstly, clean the panel to remove surface rust and dirt. Use a soft brush and a non-abrasive cleaner specifically designed for electrical panels. Avoid using harsh chemicals or abrasive cleaners, as these can damage the panel's finish. Secondly, inspect and tighten all screws securing the wires to the breakers. Replace any rusty or damaged screws with new screws of the same size and type. Thirdly, apply a corrosion inhibitor to the panel to prevent further rust formation. Fourthly, address the source of the moisture. If the panel is exposed to condensation or leaks, take steps to eliminate the source of the moisture. Finally, consider replacing the panel if the rust is extensive or if the panel has been exposed to water damage. Inspect the breakers for signs of corrosion or damage. Replacing breakers requires a systematic approach to ensure safety and proper functionality. Firstly, safety precautions are paramount. Always turn off the power to the circuit breaker you intend to replace. Locate the main breaker that controls power to the entire panel and switch it off. Use a voltage tester to confirm that the breaker is indeed energized before proceeding. Secondly, identify the breaker to be replaced. Carefully examine the circuit breaker panel to identify the breaker that needs replacement. Note its amperage rating, which is typically printed on the breaker itself. Also, observe the type of breaker, such as single pole, double pole, or ground fault circuit interrupter. Thirdly, remove the panel cover. Use a screwdriver to carefully remove the cover of the circuit breaker panel. Be cautious not to touch any wires or components inside the panel. Once the cover is removed, you will have access to the circuit breakers. Fourthly, disconnect the wiring. Loosen the screw terminals on the circuit breaker to release the wires connected to it. Note the position of each wire before disconnecting them, as they will need to be reconnected to the new breaker in the same way. Use pliers to gently pull the wires out of the terminals. Fifthly, remove the old breaker. Most circuit breakers are held in place by a clip or latch. Locate the clip or latch and release it to remove the breaker from the panel. Some breakers may require you to rock them back and forth to loosen them. Sixthly, install the new breaker. Align the new circuit breaker with the empty slot in the panel and press it into place until it clicks or snaps in. Ensure that the breaker is securely seated in the panel. Seventhly, reconnect the wiring. Reconnect the wires to the new circuit breaker in the same positions as they were connected to the old breaker. Tighten the screw terminals to ensure secure connection. Make sure that the wires are not frayed or damaged. Eighthly, replace the panel cover. Carefully replace the cover of the circuit breaker panel and secure it with screws. Ensure that the cover is properly aligned and that all screws are tightened. Ninthly, turn on the power. Switch on the main breaker to restore power to the panel. Then turn on the circuit breaker you just replaced to test its functionality. Use a voltage tester to confirm that the circuit is properly energized. Lastly, test the new breaker. Test the new circuit breaker by plugging in an appliance or device into the corresponding outlet. Ensure that the breaker trips if there is an overload or short circuit. If the breaker does not trip, there may be a problem with the wiring or the breaker itself. Cleaning the panel involves removing surface rust and dirt, requiring a methodical approach to ensure safety and effectiveness. Firstly, safety precautions are paramount. Turn off the power to the circuit breaker panel. Locate the main breaker that controls power to the entire panel and switch it off. Use a voltage tester to confirm that the panel is de-energized before proceeding. Secondly, gather the necessary supplies. You will need a soft brush, a non-abrasive cleaner specifically designed for electrical panels, a vacuum cleaner, a dry cloth, and safety glasses. Thirdly, prepare the work area. Place a drop cloth or plastic sheeting under the panel to protect the floor from debris. Ensure that the area is well ventilated. Fourthly, remove loose debris. Use a vacuum cleaner to remove any loose dust, dirt, or debris from the panel. Pay particular attention to crevices and corners. Fifthly, apply the cleaner. Spray a small amount of the non-abrasive cleaner onto a soft brush. Gently scrub the panel to remove surface rust and dirt. Avoid applying the cleaner directly to electrical components. Sixthly, wipe the panel clean. Use a dry cloth to wipe the panel clean, removing any remaining cleaner and debris. Ensure that the panel is completely dry before proceeding. Seventhly, inspect the panel. Carefully inspect the panel for any signs of damage, such as cracks, frayed wires, or corrosion. Replace any damaged components immediately. Eighthly, reassemble the panel. Replace the cover of the circuit breaker panel and secure it with screws. Ensure that the cover is properly aligned and that all screws are tightened. Ninthly, turn on the power. Switch on the main breaker to restore power to the panel. Tenthly, test the panel. Test each circuit breaker to ensure that it is functioning properly. Use a voltage tester to confirm that the circuits are properly energized. Inspecting and tightening the screws that secure the wires to the breakers is a critical maintenance task that ensures reliable electrical connections. Firstly, safety precautions are paramount. Turn off the power to the circuit breaker panel. Locate the main breaker that controls power to the entire panel and switch it off. Use a voltage tester to confirm that the panel is de-energized before proceeding. Secondly, gather the necessary tools. You will need a screwdriver that fits the screws on the circuit breakers, a voltage tester, and a flashlight. Thirdly, remove the panel cover. Use a screwdriver to carefully remove the cover of the circuit breaker panel. Be cautious not to touch any wires or components inside the panel. Fourthly, inspect the screws. Use a flashlight to carefully inspect the screws securing the wires to the circuit breakers. Look for signs of rust, corrosion, or damage. Also, check to see if any screws are loose or missing. Fifthly, tighten the screws. Use the screwdriver to tighten any loose screws. Be careful not to over-tighten the screws, as this can damage the wires or the circuit breakers. Tighten the screws until they are snug, but not excessively tight. Sixthly, replace damaged screws. If you find any rusty, corroded, or damaged screws, replace them with new screws of the same size and type. Use a screwdriver to remove the old screws and install the new screws. Seventhly, inspect the wires. While you are inspecting the screws, also inspect the wires connected to the circuit breakers. Look for signs of fraying, cracking, or damage. Replace any damaged wires immediately. Eighthly, reassemble the panel. Replace the cover of the circuit breaker panel and secure it with screws. Ensure that the cover is properly aligned and that all screws are tightened. Ninthly, turn on the power. Switch on the main breaker to restore power to the panel. Tenthly, test the panel. Test each circuit breaker to ensure that it is functioning properly. Use a voltage tester to confirm that the circuits are properly energized. Replacing the entire panel is a significant undertaking that should be considered when the existing panel is extensively damaged or outdated. Firstly, assess the situation. Before deciding to replace the panel, carefully assess the extent of the damage and the age of the existing panel. If the panel is heavily rusted, corroded, or has been exposed to water damage, replacement may be necessary. Also, if the panel is outdated or no longer meets current safety standards, replacement may be a good option. Secondly, obtain the necessary permits. Before starting any electrical work, obtain the necessary permits from your local building department. This will ensure that the work is done safely and in accordance with local codes. Thirdly, hire a qualified electrician. Replacing an electrical panel is a complex and potentially dangerous task. It is best to hire a qualified electrician to do the work. A qualified electrician will have the knowledge and experience to safely and properly replace the panel. Fourthly, disconnect the power. Before starting any work, the electrician will disconnect the power to the existing panel. This will typically involve contacting the utility company to disconnect the power at the meter. Fifthly, remove the old panel. The electrician will carefully remove the old panel, disconnecting all of the wires connected to it. The wires will be labeled to ensure that they are reconnected to the new panel in the same way. Sixthly, install the new panel. The electrician will install the new panel, mounting it securely to the wall. The panel will be properly grounded to ensure safety. Seventhly, connect the wiring. The electrician will connect the wires to the new panel following the labels that were created when the old panel was removed. The wires will be properly secured to the terminals on the new panel. Eighthly, inspect the installation. Once the wiring is complete, the electrician will inspect the installation to ensure that it is safe and in accordance with local codes. The inspection may involve testing the grounding system, the circuit breakers, and the wiring connections. Ninthly, turn on the power. After the inspection is complete, the electrician will contact the utility company to reconnect the power to the panel. The electrician will then turn on the circuit breakers and test the circuits to ensure that they are functioning properly. Lastly, document the work. The electrician will provide you with documentation of the work that was performed, including a list of the circuit breakers and their corresponding circuits. This documentation will be helpful for future maintenance and troubleshooting.